Why in the world is Mr. Cavanis teaching us chemistry? I thought this was biology class. Well, the truth is the field of chemistry and the field of biology, those two are inextricably linked. You cannot fully understand living organisms unless you understand how they are composed, what they are made of. And of course, living organisms are made of cells, and cells are made up of what we call organic macromolecules or biomolecules, proteins, fats, carbohydrates, DNA. And those large complex molecules are made up of smaller molecules, which are made up of atoms. And chemistry is really the study of how atoms interact and bond with one another. Technically, chemistry is the study of matter and changes in matter. So we have to understand a little bit of chemistry before we can fully appreciate how biology works. And so I'm going to begin by quickly going through some vocabulary. I'm going to go through these pretty fast because we're going to come back and discuss these in more detail later. But you do need to know these definitions. So make sure you're taking some good notes as we go through, and you can stop the video and back it up if you need to. So I said chemistry is the study of matter and changes in matter. What is matter? It's anything that has mass and volume. In other words, anything that has mass and takes up space. Well, that's everything, right? I mean, that's the air in this room. That's all the stars in the galaxy. That's every object you've ever touched. You yourself are composed of matter. It's everything. That's anything. And anything that's composed of matter, which every object is in the universe, is really made up of atoms. An atom is the simplest particle, the smallest piece of an element that retains the properties of that element. Now, what the heck does that mean? Well, it means this. It means that one atom of, let's say, carbon is the smallest piece of carbon that can exist. An atom of sodium is the smallest amount of sodium that you can have. That's what an atom is. The smallest, simplest particle of an element that retains the properties of that element. So what are elements? Well, I've given you a few examples here: carbon, hydrogen, sodium. There's a lot of different kinds of elements, but an element is any substance that cannot be broken down chemically into simpler kinds of matter. Now, that may not be all that of a helpful definition, but here's what we're talking about. When we talk about elements, we're talking about this. You've seen this before. This is the periodic table of elements, and every block, every little symbol that's listed on this table is a different kind of element. So if I start up at the upper left-hand corner, we have hydrogen. Over here is helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, and so on. Well, in chemistry class next year, you'll learn everything there is to know about all these different kinds of elements, and you'll learn about how this table is organized. These are not randomly listed here. This is a very organized way of listing these elements. But here's what you need to know for biology. For the most part, all of the elements that are biologically important, that is, the kinds of atoms that make up our cells, our proteins, our DNA, those are found in the pretty much the first 4 rows. So if we go 1, 2, 3, 4, here's potassium and calcium. Over here we have zinc. These first 4 rows contain all of the biologically important atoms, and some of the main ones that we'll be talking about are hydrogen and carbon and oxygen and nitrogen. So those are different kinds of elements. Remember, the small, simple pieces of those elements are called atoms. And when atoms combine, they make up molecules. So a molecule is a combination of two or more atoms held together by chemical bonds. Now, sometimes a molecule can also represent a compound. A compound is a substance composed of atoms of two or more different types of matter. So, for example, H2, which is hydrogen gas, that's a molecule. It's made up of more than one atom, but both of the atoms are the same kind of atom, hydrogen. Or oxygen, for example. O2 is oxygen gas. That's the breathable part of the air. That's what sustains life when we breathe. That's a molecule. It's made up of two atoms of oxygen that are bonded together, but it's not a compound. Water, on the other hand, is both a molecule and a compound. It's a compound because it's made up of at least two, and in this case it is two, different types of matter, hydrogen and oxygen. It's a molecule because it's made of more than one atom. You see that a water molecule is in fact made up of three atoms, two hydrogen atoms and one single oxygen. So it's possible to be both a molecule and a compound. It's also possible, like in the case of O2, to be a molecule but not a compound. So that's sometimes confusing for students. We're going to talk later about the importance of ions. Ions basically start out as atoms or groups of atoms, but they undergo a change. An ion is an atom or group of atoms that has either lost some electrons, sometimes just one, or it has gained extra electrons. An atom or group of atoms that has either a positive charge or negative charge because it has either gained one or more electrons or lost one or more electrons. Sodium ion, chloride ion, this is calcium ion, which has a double positive charge, just for a few examples. Now we're going to be talking a lot about atoms, and so it's important that you understand what atoms are exactly and how they are made up. Now, I need to put in a disclaimer here. I'm going to tell you some basic facts about atoms, and when we get to the actual drawing of atoms, what they physically look like, some of what I'm going to show you is not entirely accurate. I'm going to be showing you what's called the Bohr model, B-O-H-R, Bohr model of the atom, which is kind of a two-dimensional, simplistic way to draw atoms. And it completely works for biology. It's completely adequate. But your chemistry teacher next year will show you some more complex and really more accurate ways of representing atomic structure. But I'm going to teach you enough atomic chemistry to get you through biology. That's my goal here. So subatomic particles are the tiny particles that make up atoms, and you've heard of these. I know you've heard of protons, neutrons, and electrons. So let's talk a little bit about these. Proton is the first type of subatomic particle. Protons are located inside the nucleus of the atom. That's the central core of the atom. Each proton has a mass of 1. You don't really have to worry too much about what this unit is, the Dalton. It's a tiny, tiny, tiny fraction of a milligram. It's an incredibly small amount of mass. But a proton has a mass of 1. That's important to know, and it has a positive charge. Electrons, notice some differences here. Electrons are not found in the same place as protons. Protons are in the nucleus. Electrons are not. Electrons are found in a cloud outside of the nucleus. And electrons are so tiny, and their mass is so incredibly small that essentially it's 0. Technically, they do have some mass, but it's such a small amount that we don't even include the mass of the electrons when we're calculating the total weight of an atom. It's really, really basically zero, but the electrical charge is important. It's a negative charge. So protons are positive, electrons are negative. All atoms start out with the same number of protons as electrons, so that the positives and negatives balance out. The third type of particle that makes up an atom is the neutron. It gets its name because it is neutral. That means it does not have a positive charge. It does not have a negative charge. But it does have one thing in common with the proton. Both the proton and the neutron are found in the nucleus of the atom. And they have something else in common. They have the same amount of weight or mass. That's a mass of 1. So if I want to know the total mass of an atom, I need to know the number of protons, and I need to know the number of neutrons. If I add those two together, I'll get the total mass of the atom, because remember, electrons essentially are mass-free. Okay, so these are important. These are the 3 types of particles that make up atoms. Okay, earlier I showed a picture of the periodic table of the elements, and it's kind of overwhelming when you look at that if you've never studied it before, because you have, there's literally hundreds of different kinds of elements, and each one has a little square box with a symbol and some numbers, and usually there's more numbers than what I have represented here. But I wanted to help you focus on what is really important. When I look at a periodic table, and specifically here I'm looking at phosphorus just as a random example, okay, what does the periodic table tell me about this particular element? And specifically, how can I take the information that's given to me here on the periodic table and use that information to draw an atom of, in this case, phosphorus? So you need to understand what these numbers mean. And like I said, sometimes there's extra numbers on here, but the 2 important numbers that you really need to focus on are this number, which is usually in the upper right-hand corner. Sometimes it's in the upper left-hand corner, depending on which periodic table you're using. And then there's always a number underneath the symbol. This is the symbol, by the way. It's just the letter that represents the element. So what do these numbers mean? Well, in this case, we have the number 15 here. That's called the atomic number. And it's very simple. It means how many protons are in the nucleus of the phosphorus atom. That's it. That's what it means. Don't make this harder than it is. Sometimes students get confused by this, which is understandable if you've never studied it before. It can be confusing. But the atomic number simply tells me how many protons, that's the little positive pieces, are inside the nucleus of a phosphorus atom. That's called atomic number. And that number never changes. That's really what makes phosphorus phosphorus. If I change the number of protons, it's going to be some other element. It won't be phosphorus anymore. Okay. Another number that's important is this number right here, which is the atomic mass. It's also sometimes called the mass number. And remember, atomic number was simply the number of protons. Well, the atomic mass is the number of protons plus the number of neutrons. Okay? The other thing you need to realize about atomic mass is we can always take the number that's given to us on the periodic table and round it off to the nearest whole number. Okay, we're going to round it to the nearest whole number. Now this is 30.97, so you don't have to be a math genius to realize that this is really 31. We can round this off to 31. So if I do a little quick math here, if I know the atomic mass is 31, and I know that because it says it right here, I just rounded off this number. And if I know the number of protons is 15, I know that because it says so right here, I can really easily figure out how many neutrons are in the nucleus of a phosphorus atom. It's like the simplest math you've ever done. It's mass minus protons will give me neutrons, or another way to think of it, 15 plus blank equals 31. So you can probably do that in your head. If not, take out a calculator. But anyway, you know that number is going to be 16. So each atom of phosphorus has 15 protons, 16 neutrons. That adds up to an atomic mass of 31. Now, understanding what these numbers mean and understanding this little mathematical equation are very important when you get ready to start drawing atoms. And you're going to have to be able to draw some simple atoms in my class. So atomic mass is equal to the number of protons plus the number of neutrons. So let's take these numbers now and let's put them to use. Let's draw a simple picture. This is called the Bohr model, or the planetary model of a phosphorus atom. And I'm going to begin by drawing a circle. I want you to draw this in your notes. I'm going to draw a circle. Inside the circle, I'm going to put a P for protons and an N for neutrons. And I'm simply going to write the number of each. Now remember, where did we get those numbers from? 15 protons. We did a little math to figure out 16 neutrons. Okay? That's the nucleus of the atom. Now the electrons are out here. They're outside of the nucleus. And this is where it gets a little complicated, because really electrons exist in what's called an electron cloud, and how they move around in that cloud is very complex. But to keep it simple, we're going to draw electrons almost as if they're orbiting around the sun, like planets going around the sun. This is why this is sometimes called the planetary model. So I'm going to draw a ring around the nucleus. This ring is called an electron shell. Sometimes they're called energy levels, but I think we'll just keep it simple. We're going to call this an electron shell. And we're going to place electrons. Each little lowercase e is one electron. Okay, we're going to place the electrons in this electron shell. Now, there are some rules, and I cannot begin to explain why these rules are the way they are. I'm not a chemistry person. I know just enough chemistry to make me dangerous, so I can't tell you why. But I can tell you this: only 2 electrons will fit in that first shell. Now, this is probably a good time to mention or to remind you of something I said earlier. The number of protons must equal the number of electrons, because protons are positive. They have a positive charge. Electrons are negative. So we want this atom to be electrically balanced. We want the number of positive charges to equal the number of negative charges. So we're going to have to put 15 electrons to match up with the 15 protons. But remember, this first shell only holds 2. So we're going to draw a second shell. This is the second electron shell. And there's a rule that comes into play that says it can only hold a maximum of 8 electrons. So there's 2, 4, 6, 8. Remember, I already had 2 in the first shell, so that's 10. We now have 10 electrons, but remember, we got to have 15. So here comes a third shell, and it can hold up to 8. Sometimes it can hold more than 8, but we only need to put 5. 1, 2, 3, 4, 5, because we can only put 15 total. So remember, the first shell holds 2, the second shell holds up to 8, but never more than 8, and then the third shell basically holds whatever electrons we have left over, which in this case is 5. That's a phosphorus atom, and I can draw that based on just this information, which I get from the periodic table. This told me how many protons. We used the atomic mass to figure out how many neutrons. And then remember, the number of protons total, which in this case is 15, has to equal the total number of electrons. Okay, now throw another term at you here. when you're looking at an atom, like this phosphorus atom, the protons and the neutrons and the electrons, those are all important. But the most important thing about an atom is how many electrons are in this outermost shell. This is what we call the valence shell. The electrons that are in this outermost layer are called valence electrons. And the reason that matters is because the number of electrons in the outer shell determines whether that's going to be a really reactive, unstable atom, or whether it's going to be a really calm, unreactive, stable atom. So stability is important in chemistry because if you have an atom that is not stable, it's going to tend to form chemical bonds, ionic bonds and covalent bonds with other atoms. And so we need to be able to look at an atom and decide, well, is this a stable atom or not? But again, valence electrons refers to the outermost electrons, and in this case, phosphorus has 5 valence electrons. Okay, now, you probably need a little more practice with. So I'm going to ask you, as you're following along with me in your notes, to draw some more atoms. We're going to draw a sodium atom, and then right beside it, we're going to draw a chlorine atom. So here's what sodium looks like on the periodic chart. Notice it's Na for sodium. You think, why the heck is it not S? Well, S stands for sulfur in the chemistry world. So they had to use the Latin word for sodium, which I have no idea what that is, but it starts with an N. So Na stands for sodium. But remember the two numbers that are important. This was the atomic number, and this down here is the atomic mass. This is going to tell me the number of protons, and then this is the number of protons plus the number of neutrons. I'm going to round this off to the nearest whole number, which is 23. That means sodium is going to have 11 protons and 12 neutrons. 11 plus 12 adds up to 23. Okay. Now, if you're confused about that, go back, rewind the video, and go back and watch the earlier part where we talked about how to do that simple calculation. Now, a sodium atom, here's the nucleus. Remember, when we start putting our electrons out here in those electron shells, the total number of electrons has to match the total number of protons. We have 11 positive protons, so now we're going to have to put 11 negative electrons. Do you remember how many electrons go in the first shell? Only 2. How many go in the second shell? 8. Well, we're pretty close because remember, we only need 11, and we've got 2 plus 8 more, that's 10. That means the third shell on a sodium atom only has 1 electron. Sodium only has 1 valence electron. And a moment ago, I was telling you that valence electrons are really important because they determine whether or not an atom is stable. So how do we make that determination? Well, there's something in chemistry called the octet rule. And the octet rule says an atom, like sodium, will not be stable unless its outermost electron shell, that's the valence shell, is full. Well, it's called octet rule for a reason. As you know, oct means 8. So for most atoms, what we really mean by this is that the valence shell needs to have at least 8 electrons. If it has 8, it's stable. If it has less than 8, it's not. Now, there are some exceptions to this rule because some atoms are so tiny that they only have 1 shell and it only needs 2 electrons to be full. So, it can get a little confusing. But for most of the time, any time you have to decide in my class whether an atom is stable or not. All you're going to ever have to do is look at the valence shell, the outer shell, and ask yourself, does this outer shell have 8 electrons? And if it has less than 8, it's not stable. Sodium only has 1. So sodium is not stable based on the octet rule. And all that means is that a single sodium atom by itself really cannot exist. Sodium needs to do something to become stable. Sodium needs to interact with some other type of element to become stable, because unstable atoms really cannot exist beyond just a brief instant in time. They have to become stable. So very often, not always, but very often, what sodium does to become stable is it will interact with an atom called chlorine. So let's draw chlorine. What I'm going to do is, if you've got room to do it in your notes, right beside your picture of sodium, right here, let's draw a picture of a chlorine atom. 17 protons. Now this is interesting. Atomic mass, remember this was atomic number, right here, 17 protons in a chlorine atom. But what are we going to round this off to? It's 35.4. So don't worry about these numbers. Only look at the tenths place. If that is less than 5, you're going to round down. So this is going to be an atomic mass of 35. If it was 35.5, we would round up. We're going to round this down to 35. 17 protons plus 18 neutrons, in the nucleus of the chlorine atom. I was trying to move this little box. Okay, we know we're going to have 17 electrons. And we know only 2 electrons can fit in the first shell, 8 in the second shell, and then that's going to give us 7. 1, 2, 3, 4, 5, 6, 7 valence electrons. Is chlorine stable? No, it is not, because it only has 7 valence electrons. The octet rule says you must have 8 valence electrons to be stable. Well, this can't stand. Atoms cannot exist in their unstable state for very long. So here's what will happen. If a sodium atom ever gets close to a chlorine atom, the sodium atom will actually release that 1 valence electron. It'll kind of like hit the eject button and discharge or get rid of that 1 electron in the valence shell. When that electron disappears, look at what happens next. When that electron is gone from that space, this shell is not really a physical thing. It's kind of the space that was inhabited by that electron. So when the electron is gone, the shell is gone as well. Now look at the outermost shell of sodium. How many valence electrons now? 1, 2, 3, 4, 5, 6, 7, 8. Now it is stable. But remember that electron that sodium just got rid of had a negative charge. Electrons always have a negative charge. So now sodium still has its 11 positive charges, still has 11 protons, but now it only has 10 electrons. It has 11 positive particles, but it only has 10 negative particles. And because it has more protons than electrons, sodium now has an overall positive charge. It has 11 positive protons. It only has 10 negative electrons. So it has an overall charge of positive. And we don't call it sodium atom anymore. It is now sodium ion. Now remember, poor old chlorine is still sitting over here unstable. It needs one more electron in its valence shell to become stable. So it simply takes that electron that sodium doesn't want, picks it up, boom. Now chlorine is stable. It has 8 valence electrons. We call this a transfer of an electron. Sodium got rid of it. Chlorine picked it up. It's a transfer of an electron, but that electron has a negative charge. And so now chlorine has 18 negative electrons, but it still only has 17 positive protons. So that gives chlorine a negative charge, 18 electrons, only 17 protons, and we change the name. We don't even call it chlorine anymore. We call it chloride ion. Both of these ions are stable, but they both have an electrical charge. And if you know anything about electrical charges, you know that opposites attract. Positive things are attracted to negative things like a magnet. So these two ions will stick together. It's not a super strong bond, but they will stick together, and this will now form one molecule of NaCl, sodium chloride, which is simply table salt. It's what you sprinkle on your French fries to make them taste good. This is an example of an ionic bond, a weak bond resulting from a transfer of electrons. One atom loses an electron, another atom gains that electron. Okay, that's called an ionic bond. Okay, now ionic bond is one of 4 different types of chemical bonds that we're going to discuss. So before we go on to the other 3, I wanted to go back to vocabulary for just a moment. You know, I had you write down some definitions earlier of some of the terms that we're discussing. Here's another one. In chemistry, you have to know about this term isotope, or isotopes, plural. Isotopes are alternative forms of an atom. I'm going to use carbon as an example. And each one of the different forms of carbon, or whatever the atom is, has a different number of neutrons. So to give you an example, something like 98% of all the carbon atoms in the universe are what we call carbon-12. I sometimes just call this normal carbon because most carbon atoms are set up like this. 6 protons plus 6 neutrons gives us a mass of 12. Okay, but a tiny percent, like 1% roughly, of all the carbon atoms in the universe have an extra neutron. They're still carbon. They're still carbon atoms because they have 6 protons, and it's the atomic number, it's the number of protons that makes it carbon. But in other words, what we're saying is some of these carbon atoms are slightly heavier than normal. They have 1 extra neutron packed into the nucleus, so that gives an atomic mass of 13. We call that carbon-13. There's even a carbon-14. This is really rare. It's like less than 0.5% of all the carbon atoms in the universe have 2 extra neutrons. So isotopes are different forms of the same atom, and the only thing that makes them different is how many neutrons they have. They have the same number of protons, but because they can have different numbers of neutrons, that makes their mass different. So if anybody ever, or if you ever see it on a worksheet or a test, if you just see carbon, you can assume that, okay, that's carbon-12. Okay, if it's one of these weird forms, if it's one of these weird isotopes like carbon-13 or carbon-14, they have to tell you that. So if you just see a C with no number, you can assume it's carbon-12. That's the default. But if it's carbon-13 or 14, you'll have a number beside it like this, and you just know, that it's gonna have some extra neutrons. So I really didn't have a good place to fit this into the lesson, so I just kind of threw it in here. But I want to go back now to this ionic bond idea that we were talking about before, where you have one atom losing an electron and the other atom gaining that electron. That's an ionic bond. But let's look at a different scenario. Here is, if you look at these two atoms, let's just look at the one on the left for now. This is the smallest, simplest atom in the universe. It's a hydrogen atom. It has an atomic number of 1. It has an atomic mass of 1. So that's weird, right? It has 1 proton, 0 neutrons, atomic number of 1, atomic mass of 1. So that means 0 neutrons, and it has, this 1 positive proton, and then out here it has 1 negative electron. That's it. That's the whole atom. Okay. Here's another hydrogen atom. 1 proton, 1 electron. Really simple to draw. But here's the thing. Neither one of those hydrogen atoms is stable. The octet rule says normally you need 8 valence electrons to be stable. Hydrogen really only needs 2 to be stable because this first shell only holds 2. But it doesn't even have that. It only has 1. So hydrogen is unstable. And you can't do an ionic bond here because neither one of these hydrogens wants to give up its only electron. They both want to gain an electron. They both need 1 more electron. So since they can't steal from the other, what they must do then is simply share electrons back and forth. And this is one way to draw it. So this pair of electrons is shared back and forth between the two atoms. We call this a covalent bond. It's different from ionic because it's not a transfer. Nobody's losing an electron, nobody's gaining an electron. They're sharing this pair of electrons back and forth. This makes this hydrogen atom feel like it has 2, and it makes the other one feel like it has 2, and that's enough to make them stable. As long as they stay together, and they're held together very strongly because of this sharing, they will both become stable. This is now a molecule of hydrogen gas. We call it H2, 2 atoms of hydrogen bonded together. It's a covalent bond. That's the second type of bond. And this is a very strong bond created by the sharing of electrons. Okay. Remember, ionic was a transfer of electrons. This is different. This is sharing. Here's another example. This is oxygen. If you look up oxygen on the periodic table, it has an atomic number of 8, atomic mass of 16, 8 protons, 8 neutrons. Okay, so I put my electrons on here, 2, and then 6 valence electrons out here on the outer shell. And of course, the problem that oxygen has, it only has 6 valence electrons. It needs 8 to be stable. Here's another oxygen over here, same problem. It only has 6 valence electrons. It needs 2 more. So they can't steal from each other. Ionic bond won't work because neither one wants to give up electrons. They both want to gain electrons. So what's going to happen is we're going to have a sharing of electrons back and forth right here, another sharing of electrons back and forth right here. This is going to be another example of a covalent bond. Or in this case, it's actually 2 covalent bonds. We call that a double bond. So this is a really, really strong bond between 2 atoms of oxygen. and this forms O2. This is the form of oxygen that you actually breathe, that keeps you alive, that our cells need to stay alive. And it's just covalent bonding between two oxygen atoms so that they both become stable. Now, the big difference between ionic and covalent is if it's ionic, one atom loses the electron forever, and the other one picks it up and keeps it forever. It's a transfer. It's never coming back. But for covalent bonding, the electrons are simply shared back and forth between the two atoms. Now let's look at another famous example of covalent bonding. This is one of the most important covalent bonds on the entire planet because life as we know it could not exist without water. We know water is essential for life on Earth. So a water molecule, a single molecule of water, is made up of three atoms. Two hydrogen atoms, which I have drawn here, and one oxygen atom. And none of these atoms is stable. Hydrogen needs one more electron to be stable. This hydrogen needs one more electron to be stable. Oxygen has 1, 2, 3, 4, 5, 6 valence electrons, so it needs 2 more valence electrons to become stable. And so, again, ionic bonding is not possible. So what they must do is start to covalently bond with each other. But here's an important difference between a water molecule and an oxygen molecule. In the case of oxygen, you have one oxygen atom sharing electrons with another oxygen atom. They're identical. They're both the same size. They both have the same strength. They both have the same pull on these electrons. But when you look at a water molecule, this is very unequal. This is a silly way to explain this, but I always think of this as 3 kindergartners. Think about your kindergarten class way back when you were a kindergartner and you were learning about sharing. So you got these 3 kindergartners and they're all in one of their little stations and they're supposed to be sharing whatever the coolest, most favorite toy is in the kindergarten class, the one that all the kids really want to play with. There's only one of them. And these 3 kids are supposed to be taking turns. They're supposed to be sharing this electron, this coveted toy. Well, 2 of the kindergartners, this one and this one, are regular, normal kindergarten students. But oxygen is Big Bad Bubba. Big Bad Bubba, this is his 5th straight year in kindergarten. He can't make it out of kindergarten, so he's a foot taller than the other students. He's 50 pounds heavier than the other students. When Big Bad Bubba shares electrons with little old hydrogen, who do you think's going to get those electrons most of the time? You better believe it. Big Bad Bubba. Now, as silly as that is, it's true. Oxygen has a stronger pull. It literally has a stronger force of attraction on these electrons than hydrogen does. Now, the fancy term for this is electronegativity. Oxygen has a greater electronegativity than hydrogen. That means when oxygen and hydrogen share electrons, like you see happening here and here, it's an unequal sharing. Yes, they're being shared, but oxygen is pulling the electrons toward itself most of the time. Those little electrons don't get to spend much time over here around hydrogen. So what that means is this whole molecule is going to be a little bit, just a tiny bit, unstable. The oxygen is going to be slightly negative. This little squiggly line means a partial or slight negative charge. Now, electrons are negative. So if oxygen is pulling those negative electrons toward itself, see, that's going to give it a slight negative charge. But because the electrons are being pulled away from hydrogen, and hydrogen still has that positive proton, see, when the electrons get pulled away, it leaves hydrogen with a slight positive charge. Not a full positive charge, but a slight positive. So when you look at a water molecule, it's a stable sharing of electrons, but it's not an equal sharing. Big Bad Bubba is hogging those electrons, which gives Big Bad Bubba, Big Bad Oxygen, a slightly negative charge. And it leaves those poor little hydrogens with a slightly positive charge because they don't get to have the electrons as often as they would like. And that means that the whole water molecule has a little bit of electrical charge. Negative in one spot, positive in the other two spots. So we say that water is a polar molecule. Now, let's go back for just a second. Anytime you have electrons being shared, that's a covalent bond. Anytime a pair of electrons is being shared back and forth between two atoms, not a transfer of electrons, nobody's losing an electron, nobody's gaining, but if they are sharing, that's a covalent bond. Okay? This is a covalent bond. It's a sharing of electrons. But there's two different kinds of covalent bond. If that sharing back and forth is equal, no big bad bubbas, they're sharing equally, we call it a non-polar covalent bond. But if that sharing is unequal, where one atom has a stronger pull than the other, that's an unequal sharing of electrons, and that's called a polar covalent bond. And so water, every single molecule of water on Earth is created by these internal polar covalent bonds. So here are some water molecules. I didn't take the time to draw the entire atomic structure. I just put a O for oxygen, H for hydrogen. This is one water molecule. This would be a polar covalent bond. This would be a polar covalent bond. Here's another water molecule, another one, another one. Let's say this is a single drop of water in the ocean somewhere, or maybe a single drop of water falling from a cloud in a rainstorm. In that single drop of water, you're going to have millions of water molecules, and every single one of them is going to have a slightly negative oxygen, slightly positive hydrogens. Slightly negative oxygen, slightly positive hydrogens. Okay? And so when water molecules get together, when they get close to one another, this little positive charge right here on this hydrogen is going to be a little bit attracted to this little negative charge on this oxygen. So water molecules kind of cling together. They like to stick to each other because of those opposite charges. And when you have just a little bit of clinging or sticking together between water molecules, we call that hydrogen bonding. Okay? So just to be clear, if we're talking about the sharing of electrons back and forth here between oxygen and hydrogen, that's polar covalent bonding. That's an unequal sharing of electrons. But if we're talking about that little attraction between two separate water molecules, we call that a hydrogen bond. A hydrogen bond is a weak attraction between polar molecules, or in this case, a weak attraction between water molecules. Okay? And hydrogen bonding is awfully important. The reason water acts the way it does, the reason drops of water tend to cling together as drops is really because of that hydrogen bonding that exists in between the adjacent water molecules. Now, so far in this lesson today, and I know this has been long, I hope you didn't try to watch this entire 50-minute lesson all in one sitting, but we've covered 4 important types of chemical bonds, and you need to know the difference between these 4 different types of chemical bonds. An ionic bond is a weak attraction between a positive ion, like sodium ion, and a negative ion, like chloride. And the reason this happens, remember, is because sodium lost an electron and chlorine picked it up. It was a transfer of electrons. So if you ever hear that phrase, transfer of electrons, transfer of electrons, transfer is an ionic bond. If you hear the word sharing of electrons, it's covalent. And remember, we had 2 different types of covalent. I know this is a lot. Okay, if it's a equal sharing of electrons, like oxygen sharing electrons with oxygen, they're equal, that's non-polar covalent. But if it is unequal, if there's a big bad Bubba, if one atom has a stronger pull on the electrons than the other, that's an unequal sharing. It's still sharing, it's still covalent, but it's an unequal sharing. And it creates those little tiny positive and negative charges like we saw in the water molecule. That's polar covalent. Sharing is always covalent. Equal sharing is nonpolar covalent. Unequal sharing is polar covalent. And finally, when we talk about the interactions in between water molecules, these little dotted lines that I drew in, that's your hydrogen bonding. A hydrogen bond is a weak attraction. It's almost like static clinging. It's just a little bit of weak attraction between a slightly positive charge and a slightly negative charge. So if you're talking about the bonds within a single molecule of water, if you're talking about, let me go back here. If you're talking about this bond or this bond, that's polar covalent, because this whole thing is just one molecule of water. But if you have multiple water molecules and you're talking about the attraction in between those water molecules, that's our little dotted lines here, that's hydrogen bonding. Hydrogen bonding is important because it allows water to sort of cling to itself and cling to other objects in nature. We're going to talk a lot about the importance of water in biology, but I want you to know this. I'm using water as an example of a substance that has hydrogen bonding, but there's a lot of things in biology that rely upon hydrogen bonds to maintain their shape and their function. Proteins, the shape of a protein is held together by hydrogen bonds. The DNA molecule, the double helix of DNA, when we talk about that later, it's also maintained, the shape is maintained by hydrogen bonding. So I don't want you to think that hydrogen bonding is always about water. Other molecules can participate in hydrogen bonds as well. So I know there's a lot in this lesson. You probably need to watch it more than once. At the beginning of the lesson, we learned about how to interpret the information on the periodic table. We learned about the structure of the atom and how to draw atoms. You need to be able to do that. If I give you a periodic table, you should be able to draw a magnesium or a phosphorus or a sulfur, now that I've shown you how to do that. And then probably the most important thing in this lesson is that you understand these 4 different types of bonds and that you understand their definitions, and how they're different. So feel free to go back and watch the parts that you didn't get the first time. I apologize for this being so long. And of course, let me know if you have any questions. And be ready for a quiz soon. Have a good day.